Our girlfriend. Hey, it's okay. It's all right. We're a forgiving society. Any two quantities that have a relationship, that's what we're going to investigate. Okay? Relationships. How are two things related? The value of a computer is related to its age. There's a word in accounting. It's called appreciation or depreciation. Do you think the value of a computer goes up over time?
Absolutely.
Not.
If it's super old and it's an ancient.
It's junk.
No, it's actually.
It's landfill.
Exactly.
It's junk.
What if it's from like 18, the first computer?
They had computers in 1824.
Yeah. They have like things memories.
Gotta get going. No, it goes down. Very, very rapidly it decreases in cost. Okay? I bought a desktop in 2000. That's not that long ago. To you guys it is, but to me it's not. It was $2,000. Thing's so slow it doesn't even run. It's worthless. I turn it on and I come back 3 days later and it's almost up. The price of watermelon related to its weight. Anything you buy at the grocery store in the produce section, they sell it by weight. Okay? More it weighs, obviously the greater the cost. Wouldn't make sense the other way around, would it? The time taken for a person to walk to school is related to the distance they are from school. Okay? Lots and lots of relationships. The likelihood of it raining where you live as compared to the proximity of your geographic region, as far from the ocean. It's related. We live in a really dry place, okay? At least Kamloops is. Chase, a little less so. Okay, we're far away from the ocean. If you're far away from ocean and mountains, you're away from the rain. If you're close to the ocean, like Vancouver, it rains a lot. Related, two quantities. One more example of a relation. You guys don't know this very well, but did you know the amount of time you spend working relates to the amount of money you make?
What?
You know that? Money versus time. If you get paid per hour, which is where all you guys are going to start, so you don't want to get paid per hour. You're going to want to get paid in other ways. That's how you get really, really rich, like Jimmy Pattison, right? He sits at home on his butt, doesn't put any time in, and he made $1 million in the last half an hour. Because people are shopping at Save on Foods and listening to his radio stations. Yeah, he's worth about $7 billion. Pretty much. Yeah, he owns BC. Okay, but at one point when he was a young lad, yeah, he worked his butt off, and he did get paid per time. Okay? But all we're looking at is relation of two quantities. Lots of pages, I'm going to whip through them kind of quick, okay? This could be in words. That's what we've been doing. Mapping. Function notation. Table of values, that X and Y stuff. An equation. A set of ordered pairs. X, Y, coordinates. A graph, okay? All these ways to investigate a relation. Let's look at this guy. The cost of driving a car is related to the speed, S. Did you all know that?
Yeah.
What is that saying is, the faster you drive, you're thinking, hey, I get there quicker, right? It costs you more money. Your car is burning for a less period of time, but your engine, you're revving it up, it's sucking more and more gas. Okay? If you go incredibly slow, like it takes me, I don't know, if I go at 2 kilometers an hour, that's like walking speed, from Kamloops to here, maybe it take me 9 hours, maybe longer. Okay? Now, I'm not burning that much gas, but the engine's running for a long period of time. There's a happy medium in between these two. Let's look at this graph. This is the cost of driving a car. This is the speed. According to this graph, at what speed is it the cheapest, the most economical speed to operate your vehicle? Where's the point the lowest? Right there. Yeah, that's 70 kilometers an hour. Let me ask you another question. Does it make sense to join these dots? Is this continuous data, or do you think this is discrete data? Yeah. How on earth can I get from 40 to 60? Does I just hit a button and I go into warp and all of a sudden I'm doing 60? Or do I have to travel from 40 to 41 to 42 to 50? Absolutely. It makes sense to have half points here, intermediate values. How do I get from 40 to 41 kilometers an hour? Do I just hit a button and beep? Or do I go 40, 40.1, okay? Yeah, it's continuous. It makes sense to join these lines, join these points, okay? So, that's called a graph. Cartesian plane, Cartesian coordinate. What quadrant am I talking about? Just the first quadrant. Note, that's a broken graph. This is distorted data, if you remember from grade 8. We're not going to say any more about that. Okay, table of values. You could also get the same information here. Where's this lowest? This is cost, remember. I want cost to be lowest. It's 7.5 cents per kilometer if I do 70 kilometers an hour. If I speed on the way to Chase and do 120, not only do I risk getting a ticket, which is $176, but it also costs me more money. It costs me 10 cents a kilometer in expenses, okay? How did they make this graph? Well, from this table. Yeah, everything. It depends on everything. Everything. Your tire pressure, the air resistance, the temperature of the air, okay? Do I have a tailwind or a headwind, right? Everything, yeah. Yeah, what astrological sign is above me when I'm driving? Okay, you know. Okay, ordered pairs. Notice there's no x and y here. It's speed and cost, okay? But there's the ordered pairs. It's always bracket the independent variable, comma, the dependent variable, bracket. We know that as x and y, okay? Mapping's the weird one. Okay, we're going to do some of that. All right, we didn't choose every possible input value because it's continuous. We didn't measure every single kilometer an hour because you don't want to sit there and plot this for 3 weeks. We just want the pertinent points, like 10 kilometers an hour, 20, 30, right? Okay, this you won't be doing. By the way, this is not a linear relation, is it? Does that make a line? No, that makes a nice, the word's called a parabola. That's what makes this thing a parabola, that little square there. You're not doing that till grade 11, okay? So don't worry, we're not going to be plotting any of those. We want to find linear relationships. Okay, wordage. A lot of wordage. I don't expect you to have everything I say here stick in your head today, but hopefully 10% of it does. The values of an independent variable represent inputs. You remember when you graph something? We told you values of x and said, well, find y, plot the points, okay? X was your inputs. How do you find your outputs? How do you put it in the equation and you find it, okay? And the dependent are the outputs. So independent, I would have given you some x points, right? Like this. Don't write this, but let's just, for example, I want to know what's happening around the origin, so I use these common values. Okay, and I give you some equation like, I don't know, x plus 3. That's what y is. You put in x is minus 2 and you find out what y is. Input, output. Okay? Input, output. Dependents are the outputs. In an ordered pair, the values of the first coordinate are those of the independent. Remember, an ordered pair looks like that. This says the same thing. Okay? Input, output. The first one is the input. Table of values. The independent is usually given first. That means in your questions, it's got to be given first, right? Mapping. The arrows go from the independent to the dependent. Okay? In a graph, the independent is on the horizontal axis. Let's cross out the word often, because in this class, it's always going to be the x-axis. Right? The horizontal is always x. That's what we know. Okay? The dependent's on the vertical. And in an equation, we try to isolate the dependent variable to the left. Let's look at this. Dependent variable to the left. Here's an equation. You don't know what this means yet. I know exactly what this thing means. This is a line. It has a slope of 3, and it crosses the y-intercept at -5. Okay? We're not there yet, but we will be. All right, so that's a dependent. It's also called the output. Okay? And we put that on the vertical. Note it says y, the y-axis. Right? Okay, so this is the independent. X, independent. Values of the independent are the inputs, and those are on the horizontal axis. You know x is horizontal, okay? Okay, this here, this is this mapping stuff. These diagrams show relations. This is a relation between P and Q. You have any idea what P and Q mean? I don't either. But it's some kind of relationship between P and Q. All right? No idea. Maybe it's how many pigs the queen eats. I don't know. Which one's the independent? I don't know. Let's go have a look. This is mapping. Ba-ba-da-ba-da-ba. In mapping, the arrows go from the independent to the dependent. From the independent to the dependent. So which one's independent? P is. Okay? Just got to look it up. The dependent, well, 2, that would be Q. If you know one, you got to know the other. What are the inputs? What the heck was that again? Let's go have a look. Blah, 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 blah. Oh, here's inputs. Inputs, values of the independent. Which one was independent? That was P. So what are the inputs? 5, 8, and 11. Okay, we inputted 5, we outputted 10. Okay, I'm not even going to write the outputs. You know those are these two numbers. Here's a table. Did we see something like that yesterday? Voltage and current. Volts and amps, or amperes. All right, which one's independent, which one's dependent? Go have a look. In a table of values, the independent is usually, let's say it's given first, to the left. All right, so that means this is independent. Okay, that's dependent. I'm just going to cheat a bit. Inputs, that's independent. Outputs, that's dependent. What do we call these things? Coordinate pairs. Yeah. Okay, those are points. You can plot those. Which one's which? Go have a look. Ordered pair, first one is the independent. Remember, these are always X and Y, right? The first one is the independent. But now it's not X and Y, it's B and C. But the first ones are still independent. Okay? So then you know the dependents are the second ones. Okay, I'm not going to write any more about that. Have you seen that before? That's a relationship. What does that relate to quantities? What are those two quantities? That would be the radius and the circumference. Okay? Which one is the independent? That's an equation. The independent is on the right side. We usually isolate the dependent, okay? we isolate the dependent usually to the left side. So C is the dependent. That means R is the independent. And in words, it should kind of make sense. The circumference depends on the radius. Like if I have a really small radius, I have a really small circumference. If I have a big radius, I have a big circumference. The length of the circumference depends upon the radius. Okay, that's why it's written like that and not the other way around, like R is C over 2 pi. The formula doesn't look like that, right? Because it doesn't make as much sense. Let's look at this. The amount of sap obtained from a maple tree, you know that's real stuff, not the Aunt Jemima sugar in a bottle stuff that they color brown. It actually comes from a tree. It's actually sap, right? It's maple syrup, right? They put a little jar there inside of the tree, plug a hole into it, right? And it drains out like a drop every 5 seconds. Takes a long time to gather maple syrup. That's why it's so expensive. The real stuff. Okay? Yeah, and it's runnier too. It's an acquired taste, right? If you're used to Aunt Jemima, because it's thick and probably corn syrup, and you probably might not like the real stuff. But what's better for you? Okay, the amount sap is dependent upon the time. If you say it the other way around, it doesn't really make any sense, right? Sap from a maple tree dependent on the time, right? So how much sap you get depends on how long you wait and have that container there for. Does the time it takes depend on how much sap you got? It doesn't make as much sense, right? One's an independent, one's a dependent. Try to remember this. Time, it's not only always continuous, it's always independent. Everything depends upon time. Okay? How fast you go depends on how long you push the gas in your car. Right? Doesn't make sense the other way around. Everything depends on time. So time's the independent, the height at which this maple tree is left or whatever. This is actually different, right? This is different. I'm sorry, I'm comparing the two like they're the same. The amount of sap, this is the height of a tree, let's say, okay? You know that the longer you wait, the taller it grows. Let's say it's a kid, all right? The longer you wait, the taller it grows. Usually it maxes out some height. Maybe you're like 12, 13. Then at some point later on in life, maybe you shrink a bit, okay? Everything reverses, goes back to where it started. But which one's independent? Time. So the height is dependent, right? How tall you are depends on how old you are, how long you've been on Earth, how much time has gone by. Sap is dependent upon time. Time is always independent. The sap is dependent. Okay? All right, this is what we're actually going to do. Plot. Okay, most of your assignment's this. There's an equation. Here's some inputs. We're going to input those in X and find out what Y is. What's another word for this? Substitution. Okay? If X is minus 2, then Y is, always use brackets when you substitute. What's 2 times negative 2? Minus 4, minus 5. That's minus 9. As an ordered pair, minus 2, minus 9. Okay? Every one, that's what you do. 2 times minus 1, minus 5. That's minus 2, minus 5, minus 7. This is the nice one, 0. 2 times 0 is 0. 0 minus 5 is minus 5. Okay? 1, that's 2 minus 5, minus 3. Okay, then you're going to plot these on here. Okay, I want to give you guys time to do it. We're kind of like, I like to give you at least half an hour, right? Plot the points, connect them on a grid. Okay, if it's asking you to do that, then you're going to join it. You're going to pretend it's continuous. Use the graph to determine the value of y when x is 6. Okay, so you want to look. When x is 6, what's the value of y? Say my line went like that. If x is 6, what's y? Looks like about 8. Okay, just use the graph to do it. Then double check. Well, if x is 6, can we use the equation? What's the equation? It's right there. Y is 2x minus 5. X is 6. Plug it in. 12 minus 5. Oh, it's actually 7. I guessed kind of good, didn't I? Right. Okay, it should be the same thing. All right. This relation is called, if it makes a straight line, what are we going to call it? What's the name of this? No, it doesn't say it up here, darn it. Yeah. If it makes a line, it's a linear relationship. And what other kinds of relationships are you guys going to do in Math 10? That's it. They're all going to be linear. Okay? So let's say the same thing. If something is non-linear, does it make a line? No. Not a line. Okay? That's the only stuff we're going to get. 1 to 3, 5, 7, just A, B, and 8. Let me just show you number 5 first, though, because I remember people in the past having some difficulties. Let's just do the first substitution, okay? There's your equation. Here's your input. You're going to stick it right there. Y is negative x. Negative, what's x? Whenever you substitute, you should use brackets. There's 2 minuses here. You see that? There's 1. There's 1. Okay? And then I have minus 2. Minus minus is a plus. Okay? So that's 1. Careful. I remember people screwing this up last year. Alrighty? That's it. Where am I? Here we are.